Okay, so today we're going to be evaluating the fit of a linear model. The goal in constructing most linear models is to use the independent variable x to explain or predict the dependent variable y. We know this, no big deal. The question we want to consider is how much of the variation in y can be explained with the model, meaning how far off from the actual y value is our predicted y value, or how much error is there in our equation. Okay? Before determining how much variation the model explains, it will be necessary to evaluate how much variability in the y variable. This quantity, wow, I forgot an N in there. This quantity is called the total sum of squares, otherwise known as TSS, and represents the total variation in the dependent variable y. So here's the formula that we're going to use. The total sum of the squares looks like this. This is on your yellow sheet, and this is a nice, easy formula to read. It's literally just the sum of y sub I minus y bar squared. Literally, the total sum of the squares. That's all it is. So let's get some feelings for this. So first of all, the amount of drug given. This was the problem that we worked on last class. It was talking about reaction time. So like how much milligrams of the drug that you're given and the reaction time in seconds. So the first thing we want to do is find our R value, the correlation. And if you guys will remember, that was literally just equals CORREL, correlation. And with the correlation, it does not matter which one is first and which one is second. So you can highlight array 1, comma, array 2, or if you want to switch them and do the other way, again, it doesn't matter with correlation. Okay? So our correlation coefficient is approximately 0.9927. Okay? 0.9927. All right? Now, the next thing we want to find is our R squared value. Okay? Our R squared value is literally just going to be our little r squared. So what I'm going to do is I'm just going to type in equals, and I'm going to take that and I'm going to square it. I'm going to square it. And again, I don't want that many decimals. It's going to be about 0.9854. Okay? That's our R squared value. Now, what this means, we can actually put into a sentence. So I'm going to put down here in a sentence, I'm going to merge and center that so I can have it and easily see it. I'm also going to wrap the text so it comes full circle. And I'm going to say that means about 98.54% of the variation is explained by the model. Okay? That's literally what my R squared value means. If I have the model, I found my correlation coefficient, I squared it, and I got about 98.54%. That means about 98.54% of the variation between y and y bar is explained by the model that we came up with. That also means about 1.46% is not explained by the model. Honestly, that's pretty good. Yes. One second. Honestly, that's pretty good. 98.54% is explained. That's a lot of the variation that's explained by this model. So the next thing we're going to talk about is the coefficient of determination. What we just found, that R squared valued, is called the coefficient of determination. It's denoted as R squared. And what that is a proportion. It is the proportion of variation, and what it is the explained variation over the total variation. Okay, the explained variation over the total variation. Okay, so that R squared model, the coefficient of determination, is the proportion of variation. Okay, in other words, this specific model, it says the estimated model explains about, and we need to say 98.45% of the variation in reaction time. Okay? The estimated model explains about 98.45% of the variation in reaction time. That is really good. What? It is 5.4, thank you. I know. Okay, so let's just work some examples that we are going to go over today. On number 1, it says, the table below gives the age and bone density for 5 randomly selected women. Using this data, consider the equation of the regression line, y equals b sub 0 plus b sub 1 times x. Remember, it's just y equals mx plus b, for predicting a woman's bone density based on her age. Keep in mind the correlation coefficient may or may not be statistically significant for the data given. Remember, in practice, it would not be appropriate to use the regression line to make a prediction if the correlation coefficient is not statistically significant. So on part A, it says find the estimated slope. That's all they want. Find the estimated slope, round your answer to 3 decimal places. So the first thing we need to do is we need to copy this data. And I'm going to come down here and we need to transpose it. Now to find my slope, in the statistical formula, y equals mx plus b, the statistical formula is y equals b sub 0 plus b sub 1 times x. Slope is b sub 0. And to find slope, we'd literally just type in equals slope. And we need to highlight what first according to this formula? The known y's. And according to our problem, what is our known y's? Bone density, comma, what are my known x's? The age. Okay, so again, if you're one of those people that's like, I'm keeping notes here, you can put over here and put in parentheses, that's the slope. Okay, that's the slope. And my slope is negative 0.9922. Okay, 0.9922. Now, what that means is if I were to graph this, okay, I would have, this is my age, and this is my bone density. My slope is going to look like this, negative 0.9922. Okay. Part B says find the estimated y-intercept according to our, slope is B1. I don't know what I was thinking. Slope is B1. According to our statistical formula, y-intercept is B0. And we are going to type in equals intercept. And again, you have to do the y's, comma, x's. Y's, comma, x's. Okay, y's, comma, x's. And again, if you're keeping notes, that is your y-intercept. Okay, so b sub 0 is your y-intercept, b sub 1 is your slope. That's all that it is. Now part C says, determine if the statement, not all points predicted by the linear model fall on the same line, is true or false. That's a really, really interesting, that is a really interesting question. Let's talk about that. Again, determine if the statement, not all points predicted by the linear model fall on the same line, is true or false. So let's talk about the linear model. We found our slope, we found our y-intercept. So what if I put that together in the linear model? So the linear model is going to look like this. Y hat equals b sub 0, so 381.027 minus 0.992x, right? Isn't that my linear model? Okay? That's what I found out. They want to know if every single point predicted by this formula is going to be on the same line. Predicted, not actual, predicted. Are they going to be on the same line? How would you figure out the points from this? Wouldn't you make a table of values? So we'd have our x and our y, and we could have 25 and 39 and 40. Would all of my y values based on this model end up being on the same line? Yeah, dude, that's the whole purpose of a model, So this is a very, very tricky question, and I need you to hear me. This is a very, very tricky question. So when it says not all points predicted by the linear model fall on the same line, that's false. Like, that's the whole purpose of a model. A linear model is creating a line. Now, if it said not all points that are observed are going to fall on the same line, that's true, because that's real life. But if we're predicting it, that's literally what the line is for. It's going to be on a straight line. Now, part D says find the estimated value of y when x equals 60. We're not going to? Okay, so find the estimated value of y when x equals 60, round to 3 decimal places. This right here is our formula. That's literally what we just came up with based on parts A and B. We found my y-intercept, we found my slope. So we want to figure out the value of y when x equals 60. That means we're going to take that 60 and put it in for which variable? X, but you have to be careful, because that formula that I have there, that formula is rounded. I don't want rounded. So you need to use your exact values. Here's how we're going to do that. We're going to type in equals, and then I'm literally going to do cell references. I'm going to say my y-intercept, so I clicked that cell that I have it there, plus, then I'm going to go click my cell with the slope. Okay, so it's using the whole formula, not just the rounded answer, and then I'm going to go times 60. That way I get a nice exact answer. There's no rounding involved. Okay, so find the estimated value. That means we get approximately 321.49. We want 3 decimal places, so 493. Cool? On letter E, substitute the values you found in steps A and B into the equation for the regression line to find the estimated linear model. According to this model, if the value of the independent variable is increased by 1 unit, then find the change in the dependent variable. So what we did, we already found that equation. When they want the equation, that's what they're wanting. We already found that. Okay? So my equation here is going to be y hat equals 381.027 minus 0.992x. Okay, we already have that. The second part of this question is really interesting. It says, according to this model, if the value of the independent variable is increased by 1 unit, then find the change in the dependent variable, y hat. That is focusing primarily on the slope. Okay, my slope is 0.9923. And remember, slope is rise over run. Okay, slope is rise over 1. So that's 0.9923 over 1. That is the change in y over the change in x. You guys remember that from a long time ago? Yeah. Okay, so the change in y over the change in x. It says if the value of the independent variable is increased by 1 unit, so for every 1 unit in the independent variable, what's happening to the dependent variable? It's going down by how much? 0.9923. So when they say find the change in the dependent variable, that means for every 1 year in age, bone density is going to decrease by 0.9923. Like, that is all that question is asking. It's a very complicated way of saying explain the slope to us. So for every 1 unit that we're increasing in the independent variable, what's happening to the dependent variable? That's just our slope. For every 1 year in age, bone density is going down by 0.9923. Now, depending on the problem, that might make sense and that might not make sense. Like, if you ask me, like, what does that mean? Bone density is going down by 0.9923. I have no answer for you. I don't understand if that's a lot or a little. I don't know. But, like, there are going to be some problems where you're like, for every year in age, weight is going to go up by 0.25. Listen, I can tell you what that means. Okay, I can tell you. I can personally attest to that. So some of these are going to make sense and some of them aren't. That's just how life works. Let's go to part F. Find the value of the coefficient of determination. Round your answer to 3 decimal places. The coefficient of determination, again, is just that r squared. Okay? So to find r squared, first of all, we have to find our r value. And the r value is the correlation coefficient. So correlation. And we have to go back up to our data and have the first array and the second array. Doesn't matter what order you put them in. Don't forget, with correlation, it doesn't matter. Okay? That's what we should have. And then your r squared value is literally just your r value squared. That's all it is. Okay? It's all that it is. Now again, they want you to round your answer to 3 decimal places. Boom, boom, boom. And I'm going to come over here and I'm just going to explain what it means. It's really important that we have a comprehension of what these numbers mean, so they're not just numbers to us. Okay? That means we can explain about 89.4% of the variation with the model. Okay? That means with the model that we came up with my equation that I came up with, we can explain about 89.4% of the variation. Okay? That's really pretty good. There's not very much that's not explained, that's not accounted for. That's a pretty close model is what that's saying. Okay? All right. Now, the next thing we're going to talk about is how to create and analyze a scatter plot. Okay? We're going to create and analyze a scatter plot. When we created histograms back in the day, it's really not much different and it's very quick. So, a Paramount elliptical machine provides the table below, which gives the heart rate during exercise for cardiac health based on the age of the person exercising on the elliptical machine. So it's saying if you're using this elliptical machine and you are 20 years of age, your heart rate in beats per minute should be about 160. Okay? What we're going to do, on number 1, it says create a scatter plot of the data. Let the age be the independent variable and the heart rate be the dependent variable. That makes sense. We cannot impact, we cannot affect, we cannot change the age. That's the independent variable. Dependent is what we can. So the first thing we are going to do is we are going to highlight the data. Highlight the table. Do not highlight the labels. Don't highlight the labels. It's not helpful. Do not highlight those labels. Just the table with the data. Then we're going to go up here to the top and we're going to click on Insert. And we are going to click over here in Charts. You're going to click the one that's a scatter plot. Can you guys see which one looks like a scatter plot? And when it drops down, you're just going to click that first one. Okay? That's your scatter plot. Now, clearly it's not where I want it to be, so I'm going to move it. I'm going to click it, I'm going to drag it, and I'm going to move it so it is where I want it to go. Now, again, if you're taking notes, this would be a really good place to take those notes. So, like, the first thing that you would do is highlight the table, and then I put, like, I'm specifying no labels. Next thing you do is you click Insert, and the next thing you do is you click Scatter Plot. That's all that you're doing, okay? Now, look at this scatter plot. I'm going to zoom out so we can see it kind of all at once. Look at that scatter plot. Is that a good scatter plot? Do you guys think it's a good representation? First of all, let's look at the points. So if we look at this table, as age increases, do you guys see that 20, 30, 40, 50? What's happening to the heart rate in beats per minute? They're going down. Do the dots reflect that? Yes. I think that's great. But this chart itself, this table itself, is it a good table? Is it a good representation? Do you guys like this table? Caden's shaking his head no. Why not? Yeah, dude, there's no title or labels. There's nothing telling me what the heck's going on. This is a good representation of the data, but it's not a good explanation of the data. So let's look at number 2. Number 2 says add a descriptive title for the scatter plot and label the axes. Okay, here's how we're going to do this. The first thing you're going to do is you're going to click the graph. Okay? Then, after you click the graph, you're going to click on Add Chart Element. Then after you click on that, you're going to click on Axis Title. Okay? I'm just kind of typing down that information, and then I'll show you how to do it. All right, here we go. Click on your graph. Notice I just kind of clicked up here. I didn't click on the data. I just clicked on the graph. Okay, just the graph. Then up here, you need to go to Chart Design. It's going to be over in Chart Design. Sometimes when you click on the graph, it's going to go there automatically, but just know you're going to go to Chart Design. So if you want that noted, you can do that down here. So click Chart Design. Okay? So click on the graph. You want Chart Design, and then you want Add Chart Element. That's over here on the left. We're going to use that button a lot. When you click on Add Chart Element, we want to go down to Axis Title. Axis Title. Okay? Now, when we name them, there's going to be 2 options here. First, we're going to start with the primary horizontal. The primary horizontal. That's going to show up down here. What do these numbers down here represent? Age. Age in years. Very good. So I'm just going to type age in years. Then we're going to do it again. Add chart element. This time it's the primary vertical. And if you guys watch this, I'm going to show you a little trick. When you click on primary vertical, you automatically can start typing in the formula bar and it'll change it for you. So what does the vertical axis represent? Heart rate in beats per minute. So if you type it in there and hit enter, it'll click here, it'll show up here. So you don't have to like work on being like double click, highlight that stuff, delete it out. No, just type it in the formula bar and it'll change it. Okay? What else do I need? The chart title. So go back to add chart element, and that one's pretty straightforward, chart title. And you have all of these options here. Look what happens. When you hover, it'll show you. If I hover over none, is that what we want? Absolutely not. If I hover over center overlay, it's like on top of my data. I definitely don't want that. I do want above chart. And again, I want a good descriptive chart title for this. So I'm going to say Paramount Elliptical Desired Heart Rate by Age. I make it as specific as possible with the given situation. I don't just want to put desired heart rate by age, because what is that, resting heart rate? I don't just want to put like working out, because it's only on a specific piece of machinery. And I didn't want to just put elliptical, because like it is a specific elliptical. It is just the Paramount one, okay? All right, number 3, adjust the horizontal and vertical scaling to keep the primary focus of the graph to the region which the points lie. What they're saying is if you look at this graph, all of my points are kind of like stuck together like towards the top, right? It's not a good representation. So what they want me to do is they want me to change my axes. They want to change the scaling so we can see most of the data and see how it's related to each other. So first of all, with age, with the horizontal scaling, there's like a whole section here where there's nothing. It's not great. So instead, let's change this 0 to a 10. Here's how we're going to do that, all right? We are going to right-click on the desired axis scale. So I want to change the horizontal axis. I'm going to right-click on my horizontal axis. So I clicked on my chart, but I need to right-click on that horizontal axis. Okay? Then we're going to click on Format Axis. And notice it pops up right here. And literally the first thing that you see is exactly what we need. What are the bounds? My minimum bound, I want to change to 10 instead of 0. I want to change to 10. Okay? And look, it kind of shifted it over. That's a lot nicer. It's a lot nicer. All right, then I'm going to close out of that. And now I want to focus on the vertical axis. So I'm going to right-click on my vertical axis. Right-click on your vertical axis, go to Format Axis. Now this one might take a little more thinking. I've got 0, 20, 40, 60. All of this space has nothing in it, so I think I want to start at 100. So I want my minimum to be 100. Now my maximum at 180, it's still a little bit high, so maybe like I want my maximum to be at 170. And you can like play around with this. If you want, like if you change it at 170 and like you're like, I still don't like how that looks, you can edit it as much as you want. Okay, then close out. That's a lot better. That's a lot easier to see our data. So again, if you're taking notes, the first thing we did was right-click your desired axis scale. Then you clicked on Format Axis. Okay? Number 4 says add the trend line and the r² value to the scatter plot. Okay, add the trend line and the r² value to the scatter plot. So this bad boy right here, we want the trend line for it. We want to come up with that equation. Now they gave us the points. We could go up and we could find the slope and we could find the correlation and we could write the equation, but this is Excel. Excel will literally do it for us. So what we're going to do is we're going to click on the graph. Then we're going to go back up to chart design and add chart element. We're going to go down to trend line. Do you guys see that there? And then we're going to click on linear. This is clearly a linear trend line. Do we see that? Clearly a linear trend line. But all that did was add the trend line. It didn't give me anything else that they wanted. So I want to go back to add chart element. And I'm going to go back to trend line, and I'm going to come down here to more trend line options. And it pops this up over here. Scroll all the way to the bottom, and you're going to click Display Equation on Chart and Display R² Value on Chart. Okay, all the way at the bottom. We want both of those. And you can see like it popped up here, so you can click on that and you can drag it around and you can move it somewhere easier to see. Okay, so taking notes. First thing we did was we click on graph, click on chart design, click on add chart element, then we clicked on trend line, then we clicked on linear, then we went to more trend line options, and then after we did that we clicked on display equation and display R². So again, if you don't want to type those little notes, if you think you can remember this, that's okay. I'm typing those little notes on there so that when you're like, how in the crap did I make that? I can't remember how to do this. You can come back to your practice and be like, oh yeah, click this, click that. Number 5 is nice and easy. Number 5 literally says identify the slope of the line as given by the trend line on display. You literally just look at your formula and what do they tell you that the slope is? -0.8 or 321. Like that's what the equation told us. Now number 6 says calculate the slope of the line using Excel in the data. So I want you to come in here and type in equals slope. and you're going to go up to your data, and you're going to highlight the y values, comma, the x values. What do you notice? They're the freaking same. They're the same. That's supposed to happen. That's really good. They're telling you, hey, our data is coming directly from the formulas that we use. So if you show that equation, all of a sudden that's going to give you all of this information without having you do that work. Okay? Now, number 7 says, what does the slope of the line tell you in context of the problem? So here's what that means. The slope of negative 0.8321 measures how much the dependent variable is predicted to change for every 1 unit of the independent variable. Now let's make that a little more specific. For this problem, it means for every 1 year increase in age, we predict the heart rate will decrease by 0.8321 beats per minute. I'm going to wrap that text so you guys can see it. Okay? So, on the last one, when we were talking about, like, it doesn't really make sense with the bone density, like, down 0.9921, I don't understand what that means. This one makes a little more sense. We have negative 0.8321 as our slope. That's saying every time we get a year older, our beats per minute is going to go down by 0.8321. That makes more sense to us. Beats per minute. Number 8, identify the y-intercept of the line as given by the trend line on the display. What's the y-intercept here? 177.14. So 177.14. And then again, they want me to calculate it. So equals intercept of my y's, comma, x's. Can you take a guess what it's going to be? The exact same. Like again, they're just showing you, it doesn't matter if you use the equation or the formula, they're going to be the exact same. Now they want me to calculate the value of r, the coefficient, or the correlation coefficient, based on the value of r squared. So they're not saying, hey, type in equals CORREL. They're saying, what is the r squared value that our equation, that our formula is giving us up on the table? So the value of r squared that they give us up here is 0.994, correct? They want the value of r to come from that. So I'm going to type in equals square root of 0.994. That's all that it is. That's all that they want you to do. And we get 0.996995. Then they want you to find the value of r using Excel. So CORREL. Again, come up here and your y's and your x's. And these, you'll notice something. You'll notice something. On number 10, first of all, 0.996995, and number 11, 0.996999. This second one, when we calculate it using the data, is going to be a little more accurate. So depending on how many decimal places you want to round it to, one might be better than the other. If they're saying round it to 3 or 4 decimal places, it's okay, it doesn't matter which method you use. But what else do we notice that's different here? What else do we notice that's different here? Yeah, this one right here is negative. Well, doesn't that make sense? Look at my slope. Is my slope positive or negative here? Negative. So wouldn't it make sense that my correlation coefficient has to be negative? It has to be negative. So when you are finding it, using the r squared value, you have to be smarter than Excel. Because yes, the square root of r squared gives you a positive value, but it also gives you a negative value. So to ensure, because you know it has to be negative, to ensure that it gives you that, I want you to click on it, and in front of that square root, I want you to put a negative sign. So equals negative square root of 0.994, and that'll fix it. That'll give you the value. Number 12 says, what does the value of r tell you about these two variables? It tells you that it has a strong negative correlation, which means I don't want a formula. This is a good model. That's a really good model. Okay, there's a very strong negative correlation. Number 13, the value of r squared, the coefficient of determination, is given on the display. Use Excel and your calculated value of the correlation coefficient to calculate r squared. They're just meaning take your answer from number 11 and square it. Take your answer from number 11 and square it. 0.994007, is that pretty close to what the equation gave us on our graph? Yes? That's all that they want. Okay? They're just trying to show you what you have on your graph and what you can calculate using Excel are going to be very, very close to one another. Okay? Explain what this tells you about the two variables in context of the problem. So this tells me r squared implies that 99.4% of the total variation in beats per minute from age within the sample data is accounted for by the linear model. R squared implies that 99.4% of the total variation in beats per minute from age within the sample data is accounted for by the linear model. That is really, really good. That's saying this is a very, very good, strong model. Most of the variation is accounted for. Then finally it says use your trend line to predict the heart rate during exercise for a 35-year-old. Am I going to put that 35 in for X or Y? Am I going to put that in for X or Y? Age is X. So what we're going to do is we're just going to use our cell references. Use your cell reference for your y-intercept. So I got to come up here and find it. Cell reference for y-intercept plus cell reference for your slope times 35. Use the cell references, don't round, really important. And that tells me that I should have an average heart rate of 148 beats per minute. 148 beats per minute. All right, here's what I want you to do. On number 15, on the next one, we are not going to do all of this. Okay, like this is a lot. I think you guys get the point of it. I think you understand. What I want you to do, though, is I want you to create a scatter plot and then make sure that it has like appropriate scales, appropriate titles, and appropriate labels. Okay, go ahead and create the scatter plot. Make sure it has all of that, and then display your equation and your r squared value on it, and we'll go over it in a minute. Okay, so this is what your graph should look like. We have a nice title, we have good axis labels, we have a good scale that represents our data, we have a trend line, we have the equation. Now, below are just kind of the same problems that we did with the one above that, so I am not going to go through that. Just be very careful on if they're asking you to calculate these things from the equation or using Excel in the data. But the last thing that I want to talk about is interpolation versus extrapolation. Okay, interpolation is where we find a value inside our set of data points. So if they ask you to find something inside of your data points, that is interpolation, that's okay. Extrapolation is where we find a value outside our data points. Be careful because extrapolation can give very misleading results because we're in uncharted territory. Okay, extrapolation is a lot like number 5 right above there, where it says use your trend line to predict the sales in 14 months. That is extrapolation. That is not inside of our data values, and it is not taking into an account anything that could happen. Maybe the stock market crashes and all of those technology things go out the window. That is a prediction. It is uncharted territory. That is extrapolation. Cool? All right. You got your homework.